Hello everyone and welcome to another demo of Sovereign Boot Provisioning Wizard application. This time I'm going to present you the progress of the project and what is included in the another release candidate marked as release candidate 3 of the Sovereign Boot Provisioning Wizard. So this time I'm conducting the demo on a slightly different configuration. This time I'm using some real hardware, so it's some real deal testing. And to present you the results of the project, I chose a hard kernel Odroid H4. So let's go briefly over what has changed. So let's reset the platform and wait until the Sovereign Boot Wizard application pops up during the first boot. Alright, and here we are in the main menu of the Sovereign Boot Wizard and the system is unprovisioned. Nothing changed here since the last time. However, the process how the wizard checks the bootloaders have slightly changed. So this time when the Sovereign Boot Wizard is launched and we choose to use the Sovereign Boot compatibility, then the Sovereign Boot Wizard will only present us with the bootloaders that are not signed by Microsoft keys only. So if your system has only Microsoft signed binaries, then it will likely not find any bootloaders. So make first sure that your bootloader has at least one signature that does not come from Microsoft keys and certificates. So let's see how it looks like. So right now I have a simple Dasharo toolsuite image, which unfortunately is not assigned for bootguard, so we can only enroll the image hash into the trusted database, and that did not change since the past release candidate. However, if we try to skip this image, then we will likely hit an issue that no more bootloaders are found, so we cannot provision a Sovereign Boot. So, of course, we didn't trust any image, so we cannot finalize the provisioning, of course. So let's try for now to use the regular secure boot with Microsoft certificates. Okay, so the system restored the default settings. Now let's reset. And let's investigate what boot options I do have on this machine. Alright, let's enter the boot menu. And here we have, like the Sovereign Boot Wizard detected, I have a Dasharo toolsuite, which is unsigned, so it was illegible to be shown. Then we have Microsoft Windows operating system and also some Ubuntu. The USB and Kingston disks are, the USB is with DTS as the above options indicate, and the Kingston is a dual boot image with Windows and Ubuntu. Of course, if the Microsoft certificates are enabled and enrolled, both of these options should generally work. So let's try to boot to Ubuntu first, and you will see that it boots successfully. So what we will do now, we will try to assign the shim, Ubuntu's shim ourselves, so that it appears in the Sovereign Boot Wizard. So let's wait until the system boots up. Okay, I will log in. Then open the terminal. I will enlarge some fonts so that you can see it clearly. So what I will do, first of all, I will make some backup of my current shim so that I will not lose the original one. I'm using a PyKVM session here, so I will just make use of it and paste some comments directly to the system, right, like this. So this is making me a backup of the shim. Now let's copy it to the home directory, so I'll make some different signatures with it. For signing of the shim, I will be using PE sign utility that can be installed directly with apt package manager, for example. So, but before that happens, we have to generate some key and enroll it our PE sign PKI directory. So this is what a sample command may look like. For example, this command will generate me a key with a common name my custom secure boot key and the nickname my custom secure boot. So this we will be using this nickname to identify this key to sign our images. So now let's try to sign the freshly generated key and use it to sign our shim. So now that I copied the shim to my home directory, I can directly use it and generate a signed version of the shim, right? Okay, it exists, so I have to remove the previously generated image from my previous testing, and now it should work, right? Okay. And now that we have this shim signed, we can actually show its signatures just to verify that our signature is present, right? So this command, for example, may be used to show signatures of the file. And as you can see, it contains the standard Microsoft signature, right? And then there is a new signature with with a freshly generated key, my custom secure boot key, which we generated a while ago. So now let's copy this shim signed to the ESP partition, right? Ubuntu shim X, okay, and let's reboot. If everything went well, we should still be able to boot it with Microsoft certificates because we didn't remove the Microsoft signature. I did left the Microsoft signature on purpose to show you that the filtering of Microsoft certificates in Sovereign Boot Wizard works properly. But first things first, let's verify that our shim still works correctly. So let's select the Ubuntu option from the boot menu. And yes, grep executed successfully, so it means it's still working. Alright, then let's go back to our setup menu. And since we selected to use the default secure boot certificates, the Sovereign Boot Wizard has been disabled. So we have to enable it again, and after a reset we will be able to launch the wizard. But before that happens, we have to reset the platform so that the changes apply. And then we will attempt the provisioning the second time. Alright, so this time let's choose the Sovereign Boot again. Now we have the Dashara toolsuit, which we want to skip for now. And then magically we have our custom shim already visible here. So what we want to do is to verify whether this is the actual signature of our key, for example. So we can show the key details, and as we can see, the key is called my custom secure boot key, which actually matches what we did. So the validity of this key is up to 2037. Of course, we may, for example, choose a different time span of the validity, but this is just an example. So I think it is safe to trust this key, and we can, for example, directly boot this image because we already know that there are no other bootloaders available that have different signature than those made by Microsoft. Before we do that, let's recall an issue that happened in the previous phase where when we tried to actually boot the shim, there were errors indicating a volume full when attempting to measure some variables. So this of course has been fixed, And the reason was that the TPM event log was simply overflown with measurements, and there was simply insufficient space reserved by the firmware to actually accommodate all the measurements made during the provisioning process, because every time we update the trusted signature database or forbidden signature database, it is each time measured into the TPM event log. But since the databases we extend are becoming bigger and bigger, especially when we enroll certificates, these measurements become larger and larger, and it is quickly overflowing the TPM event log. So let's try to boot this image right now by trusting it. Yes, here we have the confirmation whether we want to trust this given fingerprint of the certificate. Let's say yes. All right, so sovereign boot provisioned, and we are booting our selected bootloader. So it was shim in that case, and we saw that it successfully passed the control to the Ubuntu's grub. So you can see that the issue with overflown TPM event log no longer occurs. So let's boot the operating system and see if everything works as expected. And yes, we are presented with the login prompt. So we can log into the system. Yes, and this is basically it when it comes to presenting the new capabilities of Sovereign Boot Wizard. However, there is still one more thing for me to show you. In the last phase, we also planned to prove that the secure boot variables protection is correctly working inside this operating system. So I will now show you that these protections are actually working, and do some live testing of this protection. So, but before we do that, we will have to clear the current platform key so that we can enroll our own keys and then show that these keys are the variable service inside the firmware is actually protecting the platform key for being overwritten by, for example, an unauthorized person. So let's enter the setup. Secure boot configuration, custom mode, PK options, and let's delete the PK, confirm the operation. Okay, and the secure boot was automatically disabled because we do not have the platform key enrolled. So now we may try to boot Ubuntu again, but of course the firmware will not let us if something changed in the secure boot configuration. So we have to reset the platform. All right, so now booting Ubuntu again. And now let's enter the terminal. Okay, and what we will need to actually enroll our own PK key. Of course, naturally, we'll have to generate a key first. So we can generate an RSA2K key, and I will simply paste the command. And for that, you will just need an OpenSSL to be installed on the system. So this is just a sample PK. Okay, I have some leftovers from my testing, so let me quickly remove it first. Alright, so again, generate EFI Signature List, and then sign it. now it works. And at last we will also generate a payload that will also allow us to remove the platform key from the variables. So what we need to do is to actually assign an empty EFI signature list, which can be achieved by passing the dev null device instead of the actual signature list containing our certificate. All right. So now we can check, for example, using the EFI variables that we are in setup mode, which means that there is currently no PK in the system. Alright, and 1 means that we are in setup mode, so PK is empty, so we can actually use the EFI update var to write a new PK. So let's do this. And the command will simply write our signed payload to PK. Right, and now if we check the setup mode again, it already shows that it is 0, so our PK has been correctly enrolled. Now we can, for example, disable or rather remove the PK by writing the noPK payload, which we generated also as well. But we cannot do that because there is a need to actually change the immutable bit in the system for this EFI file, for this PK variable in the EFI variable system. So I have to issue the following command to change the immutability attribute. Yeah, I also have to do this as a root. All right, and now the operation should succeed, right? So let's check again the setup mode, and it should be 1 exactly. So what can we do now? We can try to, for example, generate a new set of keys. So this time I will generate a new key, and I will call it noPK. All right. Then we also have to generate the EFI signature lists for the noPK. Okay. And I have to sign them as well. So first the noPK, CRT, and no noPK for removal, and then the standard payload. Okay, so now we can again issue the EFI update var command, and it will write our noPK. And if we check again the setup mode, it is 0, so it means that PK is no longer empty. And now if we would like to change this key, for example, and attempt to write, for example, the older PK, it should refuse us because the old key is not signed by the new key, so it is not an authorized operation to for the variable service in the firmware. So for example, here I now use the old signed payload with the old PK key, and it will be, yes, invalid argument, so as expected. So for example, if I would like to change the key, I have to sign the old signature list with the old key, for example here PK.ESL, and let's call it oldPK.auth. Right, and now if I attempt to write this, okay, it passed because I already signed the update of the platform key with the current platform key, right? So for example, if I would like, for example, now to use the noPK to delete the oldPK, it won't work because there is no noPK inside the secureable variables. We have the older platform key inside there. So as expected, it shows invalid argument. But we can, for example, use the noPK, which is signed by the older key, and it should pass. No, it didn't. Okay, maybe I have to switch it again. No, so it doesn't work. Alright, but it already proves that the secure boot variables protection actually work properly, and no unauthorized user cannot, for example, modify the secure boot variables and change our trusted signature databases. Okay, so thank you for watching this demonstration. Of course, it doesn't went without small issues, but I probably had some small typos in the comments. However, feel free to leave feedback and suggest new improvements to the process and to the project itself. And see you soon in the next demo.